No, because then you have a BEQ, you want to see if two things are equal. It's an if statement, it's a branch, it's a loop, you can't check every one. The same reason your chemistry teacher made you do it, or they took off points, because he had too many papers to grade and he couldn't check every possible one. Just normalize. So here's an example. What's the difference between this example and that example? There's only one difference. We changed from base 10 to base 2. Is it the same? It's exactly the same. So don't get a mental block. You can totally do it. You've been doing it for so many years. 11 plus 6. This is doing it in decimal, right? The computation, 11 plus 6. In binary, this is 11. This is 6. So let's suppose that we wanted to take 11 plus 6 and use a 4-bit representation. Okay? And I'm going to make these normalized. Sorry about that. And if we normalize them first here, instead of having 32 bits, if you only had 4 bits of fraction plus 1 bit, normalize is always a 1, right? We said last time, non-leading 0. This is what the numbers would look like. Think about it this way. If you don't know that's 11, we already do, right? But if you just see this number, this is how, what number? Because you recognize it right away. 8. How many 8s is here, sitting here? About what? 1. And change, right? What this is saying, literally, is 1, 8, and not half an 8, but a quarter of an 8. What's a quarter of an 8? 2. And then eighth of an 8 is 11. That's what it means. But can we add these values together? Just like, can we start adding bit? Can I do that? I mean, what happens if I do that? Well, they're different quantity. This is not saying, you know, when we have no multiplication factor here, we have no exponent, it's actually 2 to the 0 is 1. So regular binary numbers that are unsigned, this times 2 to the 1. This is 2 to the 1, or sorry, 2 to the 0 is 1, and also 2 to the 0 is 1. So you can add them together because they already have the same exponent. But here they're different quantities. This is saying 1/8. This is saying how much? What? 1/4. So if I start to add those bits, it doesn't work, okay? I mean, to get a number, but it's not what the semantics tells us to do, right? Are you guys following me? All right. You know, I can't just add them straight. What I got to do? We have to denormalize, is response to Mr. Stetson's question. So let's do that. We're going to choose this. In this case, actually, it's choose the larger of the two exponents. So you can do either way. Okay. So here's if we shift larger. 4 is about what? About half of 8. See the half? Then what? We can add these straight away. What's 0 plus 0? Okay. What's 0 plus 1? 1 plus 1.
0.
And 1 carry plus 1 is 0. Carry a 1. 1/0. This 8. So how, without even like getting stressed out, how many 8s is this number without knowing what the answer is? How many 8s? It's about 2 8s. 2/8, not 2/8. What is that? Well, it's a 17. It's 2 8s, and an eighth of an 8 is 1/16. 17. Is that the value we want the circuit to output and store in memory? Or put into our D register when we get done? No, and you're right, and why? It's not normalized. So how do we normalize it? Shift. Left 1, so we made this mantissa smaller, which means the exponent has to get larger to represent the same value. You guys are good? So here is it written in mathematical terms. Just makes it formal and makes it generalizable. Actually, you can use any base. You see, we're doing base 2 here, but they taught you base 10 first. So here's our steps. We're going to restore the hidden bit, because remember, the fractions we're storing in our floating point have the hidden bit removed. We're going to add that, we're going to include that back in as the 1 plus f. Then we align. What type of what type of register level component do we need to do step 1? Shift register. You guys know how to build that. Component do we need for step 2? Adder. We already designed it last module. Normalize. Good question. What component will we use? You already know it. Shift register again. This shift register could go left or right. Depends on what? Depends what you need to do to get a leading 1 and nothing else. Round, okay, actually I don't even cover round, but it's there and it's not in the homework. What? Go to you.
What does it mean by normalize F3 if you already shift the
F3
in step 1 you already shift F2 so that it's normalized with F1?
Yeah, great. Picture's worth 1,000 words. We normalized F1 and F2 and here's F3, not normalized.
Oh, okay.
F3 is F3 is on the right side of the equals.
Back to the
F is the output.
Yeah.
It's on the. So I always think this way too. Here's after like whatever middle of the night type of a epiphany, right? You get these epiphanies. Everything on the right side of the equation is the RD register in mathematics. Everything on the left side is what? You got it. If you're in this building, they call it, RS and RT input operands. You go over to the math building, that's your input, and this is, domain and map. They have a different, it's the same thing, right? Output has to be normalized. I'm not going to hold you about rounding. Don't worry about it. It's actually very simple, but we're not going to worry. You actually add half and then chop off you guys know how to do it. We're not going to put it there. Then we're going to rehide the most significant bit because we know it's always 1. There's no sense to waste 32 of our valuable bits storing a number that's always going to be a 1. So let's design the hardware. Okay. It's going to be more complex than an integer adder, but it's going to have an integer adder inside. Doing it in a single clock cycle can be a little bit complex. Clock cycle, remember, can be more than 1 gate delay. Gate delay might be 50 picoseconds. What's typical clock cycle in this laptop or in your cell phone in a time? About a nano, right? Maybe half a nano. If it's half a nano, it's 2 gigahertz clock. So can we fit more than 1 gate in there? Yeah. But can we put like, thousands of gates? Maybe not. So we're going to talk about that. We're going to actually pipeline this, so we get to learn about pipelining today. Okay, here it is. And keeping us awake, flying down. The data's. Here's your input operands, and here's Jack's output. So, how's the circuit work? He has a small ALU and a big ALU. Think about our representation. You have a sign, exponent, and fraction. If we want to add 2 numbers, this is an adder, right? So don't get confused, first of all. This is an adder, and we're going to do multiply next. This is a multiplier design. We're not doing multiply, we're doing add. To do add, let's go back here. What did we say we did? This is confusing. This is, I think, right here, right? What did we do? We denormalized, right? And then we added the exponents. No, so we denormalized and added the mantises, and then we just renormalize and get the new exponent. So, good question. How do you know which of these 2 exponents is larger, right? We had 2 to the 3 and 2 to the 2. Good question. Remember BGT instruction? How did we realize a BGT?
1 register is greater than
one is greater than the other, and how would we do that with the components we already designed? Remember the ALU? Remember the Pink Floyd at the end? We had the ALU. What was inside there we had a circuit. We subtract the 2, and then you do what? You subtract the 2, and you look at what?
You look at the sign.
You look at the sign, which is which bit of the sum? Most significant bit. If the most significant bit is a 1, that meant that it's a negative result. We meant that what you're comparing to is less than, because that thing was greater than the other. So the equation must have been less than condition. Can we do that here? Yeah, we have to compare these 2 exponents. What's a quick way to get that job done with something we already have on the chip? throw it into a subtractor, an adder, and then see if you get a negative result. Then you know which of the two is larger than the other. Subtract the two, right? Let's take a look. That's how we design hardware. We understand the algorithm. So what's going on here? They take the exponent of b and the exponent of a. They put this with the so-called small ALU. That's taking 8-bit and 8-bit versus the fraction, the mantissa, is 23. It's a big ALU. But what's happening inside this ALU? It's actually subtracting the two to see which one is larger. Is the exponent difference. I make it exciting as I can. I don't know what else to do. We even watch videos and use it. Then guess what? That's some control information. Okay, for you guys, don't worry about that's the next class. You can design this, but you can even probably design it now. If this, right? We said if this number is negative, then you know what? You know that b was greater than a, because you subtract a from b. That's part of this control box. It's going to do what? What are these? You got it. To select what? Well, we want to do something. We want to shift right one of the two. One of the two what? One of the two exponents. Or what? One of the two fractions. Why fraction? Exactly. So what we need to do here, because we want to add them together, we can't add this way. We have to adjust these to get this number, right? Before we can add them. Where does that occur in the circuit? That's either, the shifting is occurring here, but either, to save, remember I said you could shift right or shift left? You can have just a shift right or just a shift left if you know the right one to shift. In this case, we make a decision using the multiplexer based on this subtraction result. You may want to shift this left, he's doing right. Shift this right or shift this right based on which one is larger and smaller. This way they're going to end up with the same exponent. Then what do? The other one's put into the ALU unchanged. Same thing we did here. All right, we took one of these. This one. Unchanged. What about this? Shifted. In this case, shifted to the right. Okay. Then what? Boy, the room's, this must be cool stuff. The room got silent. Then what? We have to add the mantissas after they've been shifted to be adjusted so they have the same exponent. You get an output. Are you done? No, because you hand in your chemistry paper, it's not normalized. They take off, right? We got to renormalize. That means it's going to go into shifter. Shift left or right. We have to make some decision what goes in here. Well, interesting. One input is the output of this big ALU, which is the mantissas. Same thing as fraction. It's two words for the same thing. After they've been added, or what is this one? Interesting. Where does that line come from?
Control. Well, that's not really coming from it.
It's called viewing angle. Jack is on it. Because we may have to ship more than once. So you may want to take the output of the shifter. The first time we take, Jack is totally on. The first time we take the output of the adder, and then after we shift it, you may want to recycle this guy back up to here and keep shifting and keep shifting and keep shifting. Can you visualize the bits flowing through here? Good question. All right. I want to take off. This actually came from the book. The author has a little partial credit deduction. There should be a tick mark here, right? This is not 1 bit. How many bits are flying over this bus? 23. Is it wrong? Well, we draw this for simplicity, right? If you drew 23 wires, yeah, actually 23 wires get built. We look for a design tool to make that mapping, and then we put it on the mask, and it's built, right? But to draw the functional view, we just write 1 wire. But we like to remind ourselves sometimes to put how many wires are in that bus. There's rounding hardware, which don't worry about it. It just adds a half and then cuts off the bits, and then we get the result in terms of what? Fraction we did. What about the x? Where's the exponent come from? What's this about? That is renormalizing. Okay? So every time, this is cool, every time we shift left to make the mantissa smaller, you wanted to increment over here. Every time we shift right, you're making it smaller. This guy it should be increment that way. Shift left should be decrement. So these things work in unison when we make just the same thing, pencil and paper. We want this to represent the same value. So this is getting smaller, this has to get larger, and vice versa. There's your output. We have words for each stage of that processing. We use the word stage. It's staged, right? Event is a stage 1, and a stage 2, and a stage 3, right? What's stage 1? Has a name. Compare up exponents. What's stage 2? Shift the smaller number right, or we can shift the larger number left. Next stage is add. Next stage is normalize. Next final stage is round, which I don't hold you guys for. These are usually pipelined. So what is pipelining about? So pipelining will insert registers between each stage. Why do we do that? Because this is combinational logic. Well, some of these things are. This is not, because this has a clock for the shift. But the point is, if we have two numbers to add and they're floating point numbers, two, let's say quantities to add, they're floating point numbers, we have to wait for them to propagate through this entire circuit. As you can see, it takes more than one clock cycle, especially with the shifting going on. These two locations. One way to speed up the steady state throughput is to use pipelining. So the idea of pipelining, do I have a pipeline? I think I have a pipeline. It's a previous, isn't it? It's a previous module. We'll show you. We'll do it in real time. The idea of pipeline is to break into stages, and I mentioned pipelining, right? Who is which engineers attributed? You got it, Henry Ford. Okay, so the concept is that we can put a register here and a register here and a register here at each stage, and then we can apply two inputs. They propagate through this stage. While that data is latched and applied to the next stage, it's time to put into the inputs in the next one, for the next set of inputs into the ALU for the next stage. So pipelining is a lot like assembly line manufacturing for bits. We can overlap. It's called temporal parallelism. So we have two types of parallelism. It's motivating you for the next classes is temporal. We don't hold you in here, but temporal parallelism is pipelining. And we have spatial parallelism, that's multi-core. So remember time and space trade-offs? These keep coming up. We call that parallel processing multi-core, right, as an example. What's this mean? We have different cores on the chip, and we perform the parallelism over space. When we pipeline things, we only have one instance of this circuit. We only have one instance of the small ALU. So how do we make it parallel? We break it up over time and break it into small steps. Okay. So there's some interesting things about a pipeline. We say, suppose this is broken into 5 stages. I won't draw all the boxes, but we're gonna, this is our floating point adder. And I break that into 5 equal duration stages. If it takes 10 nanoseconds without pipelining, after the first result emerges, so what we're doing is time 1, we're going to put a plus b in here. So it's in the first stage, we call S1. Then the next clock comes, the sum of a plus, well, this is like the next processing phase, right? The next phase of a and b is here. This is vacated. We can put b plus, we can put c plus d, the next pair of operands, into this first stage, while this one propagated to here. Then the next time, this is stage 2, and the next time, the first element goes to stage 3. See? A plus, the next, I'll put double of a and b, and then here, and then here. So when the first result, a plus b, emerges, is how many nanoseconds? It was 10 nanoseconds in the non-pipeline. How many nanoseconds in the pipeline? No, for a and b. Also 10 is the first result. But what about when C, so A and B came here, then C and D came next, C and D came next, so A and B popped out?
12.
Yes, at the 12th nanosecond, 10 nanoseconds later, and then 2 nanoseconds after that, you get, yeah, and then 2 nanoseconds after that, or I should go from here, 2 nanoseconds after that, you get E plus F. But wait a minute, it says it took 10 nanoseconds to add 2 numbers. How do you get an only 2? Pipeline, you get a Henry Ford. See? What's Henry Ford's idea? Okay, it's like, great, we got the Industrial Revolution, and I'm up there in Michigan, right? Anybody ever go there? Detroit? And there's rich people up there too, right? It's true, actually, these big homes on the lake and stuff, it's too cold, right? No one live there, but now we have right? We have air conditioning, right? So everybody goes to Florida, right? Or goes to, but nobody lived here, right? Nobody, I mean, some people did. We're glad you were here before we all moved here. But why did we move here? Air conditioning. Beautiful weather, actually, but before we had air conditioning, it may not be that beautiful, right? Actually, Edison, right? Anybody goes to, you go to Florida Gulf Coast, and you go down there, right? What's this city down there? Fort Myers, yeah, I go to Fort Myers, all Edison Community College, and Edison this and this and that. What was Edison's gig about? He gives the #1 invention everybody knows, right?
The microwave.
Microwave, no. Light bulbs, right? Does anybody know, if you take a history of technology class, everybody, yeah, Edison, right, light bulb? He did that for one reason, actually. He didn't really want to invent the light bulb. He had a good air conditioner, actually, and a good motor. No one wanted to buy it. He knew that if he had a good light bulb, everybody would electrify their homes, you know, like rural electrification. So actually, he spent 12 years making the light bulb so that he could sell his air conditioner because he wanted to live here in Florida. Yeah, it's true, actually. You can, if you go down Fort Myers, there's like a little plaques and stuff. Yeah, it's nerdy, right? But actually, some of it's cool, right? You read these little, just for 5 minutes, right? Let's see these things, right? But yeah, you go there, you read, like, you know, the Edison, this, and Google it. So what's the point? So the point was that turn of the century, okay, Industrial Revolution. Henry Ford was like, all right, we can make cars now, but it takes maybe 2,000 hours to make one automobile. It's never going to be profitable. So you can break in a little step, right? You're going to weld the frame. You're going to put the wheels on. You're going to do this. You're going to do that. He broke it down to about 10 minutes. After the first car came out, every 10 minutes, $200, which was like whatever, 5,000, right, in his corporate pocket. What do we do that? We do this, it's a great idea, so we do it with bits. This is a long process, we said, right? This is a long time to, a lot of steps. You know, a lot of steps to do the floating point operations here. It may not be as fast, right? We had it on the slide here. Where's that slide? Yeah. It'd be very complex to do in Boolean logic. If you try to make a K-map for that, right? It's a big K-map, actually. So it's too complex to do in one cycle, but we don't. You know what? We got Henry Ford. We just break into steps. Is it still pretty fast? Yeah, in steady state. You're watching a video, which you're probably doing, and you can see the bits fly by because you do one multiply after another, or this is adder, but one after the other. Question. Suppose Henry Ford didn't balance his pipeline, and it's still 10 seconds, but this was 2, this was 1, this was 3, and this is 2, and this is 2. It still should add to 10, right? If somebody hires you from AMD, which they hire you, to balance the pipeline, and you're designing this, which they actually design these, and you don't do a great job, you end up with one stage is 3. When does the next result come out in the steady state? It's only 1 nanosecond, right? Difference in the one stage. The rest of the stage is still fast, right? But what's going on here? There's a word, right, for it. Go ahead, speak up.
Wouldn't it be like the 3 second delay?
Yeah, this would be 3 nanoseconds every time. This is a word, right?
It's like bottleneck.
Yeah, exactly. There we go. I was going to say Coke and bottleneck. It's a bottleneck. We can only get, so there's a saying that a pipeline is only as fast as the slowest stage, which is true. Why? Because, I mean, the stuff can come here faster, but then what comes out is only every 3. The pipelines need to be balanced. If they're not balanced, so if I look in steady state throughput, what was the 2 nanosecond? So these are almost all 2, and you even made that one faster. You think, hey, I'm doing great. But actually, since this one went to 3, just even 1 went to 3, what's the relative performance of the 2 nanosecond equal stage relative to the one that has a single stage at 3? How much percent faster or slower? 50%. Did you slow the whole circuit by 50%? No, you only slowed one stage. But a pipe, so here's your takeaway. Pipeline is as fast as the slowest stage. Do you already know this? Yes, okay. I give you a chain, right? A bicycle chain, motorcycle, it has a weak link, right? We say that saying, right? Chain is as strong as its weakest link. Yeah, it doesn't matter how strong some of them are, whatever the weak is going to break there, right? This is being the bottleneck, is like the weak link on a chain. Chain for bits. Pipelining, okay? So everything's pipeline. That's actually computer architecture. You actually start to put the registers there, and you get the Verilog out, and you try these, and you start tuning your stages and pipelines. We just get you started on this. So we're going to go to multiply next. Before we do that, I'll let you ask any questions. People's brains engaged. I'm really happy today. Yeah, go ahead.
Okay, 2 questions actually. So you said that the pipeline needs to be balanced, but
Yeah.
if one of them is...
If you want the highest throughput.
Okay. Like, let's say instead of the 3, we had 2, 1, 2, 2, 2. Is that okay? Like, just, the 3 wasn't there.
You can, but then there wasn't 10 nanoseconds for this process. It was actually 9.
Okay, but is that still, like, is there a reason why we would want the other one before that to be 2 as well, like fully balanced?
Good question. Does it matter if it's 1 or 2? So if you're in your office and you say, you know what, you go to your manager and say, hey, we got our pipeline here, and I got this, I made a really great exponent different circuit, and it only does it it doesn't half the time. And are you going to be proud, or are you going to be feeling good about telling him that, or what? Because you just spent a month doing it. Here's somebody speaking. Yeah. What's that?
It's only as fast as its fastest state.
So you spent a month making that thing really fast. You got it down to 1, and then did it have any output? Did any effect? 0. Is it important to know about pipelining? Yeah. It's a perfect case in point.
And then with the when we would go, like, the rounding got stuck and you had to keep going like 0.33333, like you were saying.
Yeah, 0.33. Okay, but go ahead. Yeah. I don't put any point. We don't. So in this thing, everything is a power of 2, like a half, a quarter, an eighth, maybe a 16th. But just for hypothetical, go ahead.
Yeah, when it goes back after the big ALU, when it goes back to tell you that you need to keep going.
Oh, but that's not thirds, right? That's.
Well, yeah, I just.
Yeah, okay, go ahead. No worries.
I should have said a different number. Anyway,
Okay.
What is telling it to go back? Like, what is telling it?
There's a state machine in here.
It's just a control.
It's an awesome question, and I'd love to, because this gets cool too, to design this stuff, but if we do this, then accreditation says we didn't teach you memory systems, and then, because they give you too much. Well, we do the best we can, right? But yeah, so it's inside this box. It's a state machine. It's actually counting, and it's checking what these bits are coming out, and then how does it know when to stop? When you, I hear it. When it's normalized, when you have a leading only one bit, that's a 1 before. You can imagine what's inside that state machine. You're going to be checking mealy or more, okay? But see, too many clicks and we see energy, battery. We lost our battery. Ready for multiply? Neil.
I noticed that the hardware did not take the sign into account. So if we do take the sign bit into account, how
Sign bit?
more complicated it would be?
All right, so sign. You know, why is the sign coming from here? That's a good question. So, good question. So if you're going to add something and you get a positive or negative, it turns out if you add suppose you're subtracting. The only way we can get if they're two negative, two positive numbers, we cannot get a negative number. But anyway, this is actually doing here is actually not hard. It's the most significant bit of the normalized.
But on the input, you don't take the sign into account on top of the input.
No, we should, right? Oh, you're right. We don't. Okay. Well, so what's happening here is if it's a negative number, then what do we have to do? It's going to tell us that's actually an input. It should be an input to this control to tell us which of the mantises to subtract from the other. Because if the signs are different, you have to add one and subtract the other. So this is very interesting, which is another good insight. We always try to explain things in 5 different ways, because then you understand more, or maybe at least pick up one. So this is mixing. This sign is actually mixing the operation and the data representation. So we call it a negative number, but we only have adders here. So if it's a negative number, it means it's control information into the subtractor to subtract. Which of the two subtract? Well, actually, it's even a decision. If they're both negative, then you're going to add them, right? Because if they're two negative numbers add together, it gets more negative. So actually, what Neil is on a good track. I think it's going to actually be inputs to the control box, and it's going to control: do you want to add or subtract? Turn this into an adder or a subtract. This is no, turn into adder or subtractor of these big ALU mantises. Makes sense, right? So for human convenience, we think of sign as part of the number, but it's actually, when we want to add two numbers, it's actually telling us, do we add them or do we subtract them? It's a very good point. And we use, in this case, what gate would be, this wouldn't be too complicated, what gate would be inside this control box comparing those two? Excellent. You got it. See if they're different or not. Actually, you can use X, we have something called XOR, is a difference, Boolean difference. Then we have X NOR is what's called equivalence. So here's some coolness. X and Y. Okay, no dessert, cookies, ice cream, but not both. We call this Boolean difference detector, detection, or just Boolean difference. We call this Boolean equivalence, or just equivalence. Equivalence. Can you see the equivalence? Well, when x equals y, double equals, it's true. When they're different, it's false. When they're the same, it's true. There's only two cases when they can be the same, when two bits can be the same. So x nor, this is x nor. X nor is the so-called Boolean equivalence function. Whenever you're designing hardware and you want to see if two bits are the same, you can use a single X nor gate. If you have a lot of bits to see if they're the same, and you already have an adder on the chip, throw it into the adder and subtract them, and see and check for a 0 result. Use De Morgan's law. Turn all those inverters to check for 0, turn it to 1 into an AND gate, turn it into a NOR with De Morgan's using the subtractor. But if you only have one bit, it's going to come up in the next module. We're going to design a memory system. We have to see if the data is in cache or not. It's like some call a valid bit. To check for equivalence, we can use X NOR. Just keep in mind. Other good questions. That's a good question with this. What do you do with the sign? We're going to check if the sign's equal or not, and then we're going to make a controlled decision to say if I want to add or subtract in this mantises. It's actually mixing the control information with the number representation. Other question? Okay, let's go on. For multiplier, multiplier is exactly the same except we use the rule for multiplication. Don't get a mental block. It's just, they're just already in numbers you already know, and it's already a procedure you already know, except we're not going to write any number greater than 1. And we'll change the exponent to 2. This is just scientific notation with bits. See? And I want you to see it as a half of, it's a little bit crazy, but half of, all right, see it as a half times 4375. All right, we can get the product, battery. So add your exponents, and then we're going to multiply significance. That goes into a multiplier. Then we got to renormalize. In this case, it's already normalized, so we have a leading one. No change. And now we're here to Neil. Determine sign. What gate do you need to determine the sign? Yeah. So in this case, this is a sign of A and the SGN, right? Of X and the SGN of Y, right? Are the inputs to this Boolean table. And you XOR them together and you're going to get the sign of the product. This is the sign, SGN if you want, of P is the product of what? X times Y. Battery issues. Let's take a look. Oh, we already gave away the answer to that one. What about this? Just add the exponents. Some exponents might be negative, some might be positive. Okay, don't worry about it. We're just going to add them. Choose complement numbers. Actually, are they biased? Oh, we have to deal with the bias, right? But this is just for right now. We get you started. It's actually inside the functional element. Exponent update. It's based on the shifting amount. So every time we had to normalize the shift here, you're going to do what to the exponent? Add 1. If you're making this smaller, you're going to add 1 over here. If you're making this, this is a significant, this is a 32-bit value broken to 23. The 23-bit coming through here is going to be decreased, then you're going to make this larger. If it's increased, you're going to make this smaller. And the result is a product. So we can pipeline this at this stage, or we can even more, what we use the word granularity, fine-grained pipelining. This would be coarse-grained pipelining if you put a register stage here and a register stage here, and you set the clock to the max of any of these stages. See, that's the point. You have to set the clock to the max of any of the stages. So if you make one stage faster, you still have to clock it at the stage of the speed of the slowest stage, time of the slowest stage. because otherwise you're losing data before it's ready to come out. So if you do coarse grain, it's not going to be too fast. But I can use, I'll write it up here because I'm saying a lot of words and you're probably like, what? We have coarse grain and fine grain. Pipelining. Anybody want to take a guess what the difference between those are? Anybody have a water softener? They're students, right? It's an apartment. You go to Lowe's, Home Depot, and there's these big bags of salt. What is that for? Your water softener. It's a coarse grained, right? It's not like little granules, right? It means a granule, right? So we can put a register stage here and there, and we're done. That's 3 stages. But inside each one of this, right, we had, especially the multiplier, we had a whole bunch of adders, right? You can make each one a stage. That's fine grained. Which is going to have higher throughput? Good question. What's throughput?
Coarse grain.
No, fine grain. But fine grain, because we can, once we go through one stage of the multiplier, it's next time to introduce the next inputs. So in steady state, we're getting an output at the time of this little tiny stage instead of waiting. In other words, if Henry Ford wanted to make more money, how would he do that? If time versus space trade-off, okay, there's a lot of cheap land up in Michigan, so then what do? You make the pipeline longer, right? So each stage takes, instead of 10 minutes, now it's 8 minutes, because he's not going to weld the whole frame, he's just going to weld this beam, right? And then the next guy's going to weld the next beam, right? What do? You made the pipelining more fine-grained. Guess why? Because then in steady state, once the first car comes out, you get the next output sooner, so it means the throughput. What's throughput? Units of throughput. Is throughput a time metric or a rate metric from module 3? It's always a rate metric. It's outputs per unit, in this class, is outputs per unit time is throughput. But, as Miguel said, right, if it's coarse-grained, if you're just doing a one-off, in this case, floating point multiply, did it matter if it was coarse or fine? No. It takes the same time for the first output. What do you mean first output? Anytime I do a multiply, there's going to be a first time for everything, I guess. So the first time that you do a multiply, that takes the same amount of time no matter if it's fine-grained, coarse-grained, or unpipelined. So the only time we get benefit of pipelining, right, is if what? If we have a multiply after a multiply after multiply after multiply. If you just do a multiply, then you do a bunch of load store and go over the program, and you don't do another multiply for a while, it didn't matter, it was pipelined. You see my point? We have to keep the plant busy and going. Any other questions on this one? Oh, good. What?
I'm having a hard time visualizing how making a finer grain pipeline would make.
Yeah, okay, so finer grain pipeline means that this is a multiplier, and in there we have different ways. So if we had, let's say, the AND array, you're going to make a bunch of AND gates, and in one clock cycle get all the partial products, and then add them up in a tree.
So it's like parallel processing.
It is, exactly parallel. I just erased it. What kind of parallel processing was it? Spatial or temporal? No. I wrote it on the board. Temporal, yeah, it's temporal. It is parallel processing. It's temporal parallelism. You're right on track. So do you know how it makes it faster? Because each step now is just a tiny little, instead of waiting, like a multiplier might take, to go through all those, the whole tree, right, might take 200 nanoseconds, but to go through one level of the tree only takes 2. So if you make it fine grain pipeline, then you're only waiting 2, 2, 2. The 2, it's ready for the next. It's ready for the next, right? Right? It's just like you get your, I don't know, you go to, what's your, because it's lunchtime, right? I'm on some food. Right? You go to your restaurant, right? What do you like? I don't know. Subway, no, it's old school, right? Now they recast these things. Actually, Chipotle is the Subway, right, of Mexican, right? It's no. My friend's a business student. When they were like, their stock kept going up, and like that's what they taught them. It's like, you know, the people that started it is like McDonald's bought it but they said that, you know, McDonald's is, well, people think it's not healthy. So then it's like, well, what can we do? Well, everybody thinks Subway's healthy, but Subway's already got the sub market because even they got the name, right? Subway. And so what can we do? We'll make a pipeline for making Mexican food, right? So you go there, right? What do you want to sell, right? Right? Suppose there's like, they ask you, you know, do you want this, this, and this? The more people ask you, if you can walk fast enough, that's why they pipeline it, so they can sell more, whatever taco salads. It's pipeline. Does it make sense? Fine grain. Fine grain, so that's a good extra credit or something. I don't know. I'll put it extra credit. Fine grain would be more, I don't know what their job title is, more food handlers at Chipotle is a fine grain pipeline. You have a higher throughput, but not a
higher speed for a single.
You got it. You know, we actually call that latency. And we talked about latency in terms of data transfer, but this is latency of a computation, is the time for a one-off, isolated execution of that instruction. So pipelining does not decrease latency, but it increases throughput. Sounds like a contradiction, but actually it's, you see it every time you go to Chipotle. Yes, sir.
So if you know that it's going to have a lot of outputs,
Yeah.
screening is better
Yeah.
in the end, and then for screening is better like
Yeah, because actually there is an expense with putting all those shift registers in there. That's a lot of gates, and it's going to take more energy the more you fine grain you put. See, right? Because Chipotle has to pay more employees, right? If they want to fine grain your taco salad, they got to pay more employees. And so guess what? Then if people don't come to it's not a busy store, you know, it's out in the middle of Narcoossee or somewhere there, and then they just hire one employee, right? They don't bother to pipeline it. Okay, and we have no click. So this is kind of a summary wrap up, and then we're done here. This is saying some questions that always come up, okay? And how do you represent the value of 0? 0 has a special representation because we always have a hidden 1, right? So even if you set the fraction to 0, it's always 1. So how do you represent 0? So 0 is reserved when you have both the fraction and the exponent to be 0, okay? And then there's some other things here, this is some coolness. This is the difference between range and precision on the number line. So if this is 0, you can think about this as the smallest value you can represent. And this is basically determined by the number of bits in which field? In the exponent field or the number of bits in the mantissa field? This distance. Mantissa or exponent? Blue is mantissa or exponent? Mantissa. Because you're saying your basic granularity, right? You're breaking this. You're actually doing analog to digital conversion, right? Because the number line is analog, it's continuous, and we're making it digital, which is I'll just get that here because sometimes people come to me and say, what's the difference between analog and digital? But we should know, right? But I want you to know. So digital is the classic example, the best one I can think of, right, is a ladder. You're either on the first rung, or the second rung. You cannot step halfway between the two rungs. You're going to say, well, why can't it be halfway? It's quantized, okay? Quantum physics, quantized. This is choice. What's a classic example of an analog would be a thermometer, right? Whatever temperature it is, you buy a little bit better thermometer, you get another more accurate reading. Did you change the temperature? No. You're just measuring it to more precision. It's actually analog value. It has an infinite number of bits of representation. So here we don't have an infinite number of bits. How many bits do we have? 23. So this is going to tell you what's the resolution here, but what about the red? Range. Suppose I want to represent a number that's bigger than the highest exponent can get to. We call that overflow. What happens when you have a number that is too tiny to represent in 23 bits of fraction? You've underflowed. Sorry, we don't have a click today. Well, maybe I'll fix it. So what's the takeaways? We're done with this module. I'm just going to have a click, so we'll go over. So floating point arithmetic on hardware supports addition, subtraction, multiplication by breaking the data representation into fields. We still have 32 bits, but now the bits have different meaning. Someone in the last class in the other section says a really insightful takeaway. You know, if I'm looking at these 32 bits, how do I know if it's float or not? You don't. Someone has to tell you that that's a floating point value. They could even be what? Those 32 bits could be an unsigned binary number. They could be a 2's complement binary number. They could be float. It can be an instruction. How do you know? You don't know. So actually, the meaning of the bits is not associated with the value that it represents. That's how we interpret it. How do we keep track of it? Well, we do some things to help, right? We organize memory in segments. Remember text segment, data.text. The data segment means that everything there is a data value. It's not an instruction. Don't try to execute it. You get segmentation fault. You're in the wrong segment. It's a fault. You're at fault. The processor's at fault. What about floating point? Floating point, we're going to break it into these different fields. The word is derived from here. I never read that in any book, but after it was an epiphany moment, oh, you allow the point to float. It's a floating point, floating binary point. It is true. Each field is computed using integer. That's really interesting. We're doing fractional math using integers. How do we do that? Scientific notation. These usually require several clock cycles, okay, and then digital representation of numbers is an analog world, right? Where we especially when we listen to Pink Floyd, we exist in an analog space or something, right? But everything we put inside our machine has to be turned to bits. That's analog to digital conversion. Any idea how? I know maybe you guys haven't taken a. We're going to what would be one way to converting an analog number into bits? Good.
Fourier transform?
Fourier transform is already, well, we work with continuous quantities, but Fourier transform will go from time representation to frequency. It doesn't change bits to analog. We're not changing the precision. Basically what we're saying is a frequency domain versus time domain. It's on the right idea, but
Like a wave, like a sine wave, you want to convert it to like a square wave.
so you can convert sine wave to square wave. I'm thinking of their basic electrical devices. If you have a resistor tree, right, like a voltage divider, you can take a tap at each point between the resistors, and then you know you've converted that. You want to look? We convert the analog value into bits. And then we can go the other way. We can convert a binary number. We can do digital to analog conversion. Is this a waste of time or cool? Oh, good. Okay. I think it's cool. I'm ready for a new module, right? So we get a chance to take a break. Let's do analog to digital. It's ADC. And maybe we get lucky. Let's see. So what's inside this box? They actually have a tree of resistors, and they're basically looking at the output of all these different steps. There's different ways. There's all kinds of decimating, and they keep dividing it. But here's getting the basic idea. Okay. Successive approximation. There's different ways of doing it, but you take this number and you actually figure out, you guess what it is, you subtract the difference. This is instead of using an ALU to subtract, we're actually using current mode and adding the two currents together and getting the difference between the two signals. So Fourier transform is a little bit different concept. Fourier transform, I don't expect you guys to know this, you haven't taken the class, but this motivates you to take. Fourier transform is going from time domain to this frequency domain. And this is a great picture for that, and I'll show you here, probably will come up right away, is taking a sine wave and making the pulse train, see? So one way to compose an arbitrary signal is to superimpose sine waves of different amplitudes and frequencies. It turns out in the square wave, if it's very square, you have to have infinite frequency to achieve this type of but actually if you add these together you get a harmonic, right? And you add multiple you add multiple waveforms together, and what this is telling you is you have yes, this frequency is present in the waveform, yes or no, and what's the density of this frequency domain. So what's the example? Would be they call it beat frequency. So any musicians here? Musician? Somebody's always asking me musician. Who's that guy? Yeah. So what's a beat frequency? BPM, yeah. So beat frequency is if I have two tuning forks, right? And you hear like the two of them, they're interacting. That's when the waveforms add, and when they subtract, they're actually going on their own speed. They're not oscillating, but you hear an oscillating tone is the beat. So what this is doing is taking fixed frequency of sine waves and adding them together to get a beat frequency, which is like the interaction of those. That's Fourier transform.
It's a cool video if you Google Fourier
Good.
series.
Let's do it.
Animation using circles.
Awesome. Let's do that. Fourier transform
Yeah.
using.
It's formed using circles.
Okay. So this is a great thing about, see, in the old days, you had to go to the library, get a book, using circles. Let me just type this guy.
Yeah.
Introducing Zeus, first truly smart car charger.
All right. So this is, okay, this is way coolness, right? See? Okay. So this is a very interesting thing. I never forget it. And actually, remember demonstrations in physics class? Okay, in high school, definitely the coolest one's a Van de Graaff generator, right? Or chemistry, sometimes you get colors and stuff, but flames and things. But another cool one in physics was a professor took a projector, which just had a light, and he had just this arm with this rotating in a circle. And if you look in this dimension, this thing's rotating in a circle in this dimension. Look at my hand, what is it? If I do this and I trace it out, it's actually making a sine wave. And they never teach you this, and I got so mad because I was studying all these, sine, cosine, and you do all the derivatives of these things, and you relate to circle, right? They always tell you sine and cosine, the x and the y on the circle, which we're looking at, right? But they never make the connection that if something is in a three-dimensional space, moving like this, and I graph my position from the axis here as this circle goes, it's actually a sine wave.
Going up and down.
So anytime we see, this is very interesting. So that's like stuck in my mind. I never got a chance to, in my retirement or something, I'll take some quantum physics class. Because I think anything that oscillates with the sine wave is actually rotating in a circle in another dimension, right? Like a parallel universe or something. It has to be. It has to be. We can see that over here. Okay, so what we're doing, right, is graphing the x and y. You can think about that. I mean, it's kind of cool, actually. But so here, we have three different amplitudes. See, can compose the three different at different frequencies, because this is higher frequency, right, and lower frequency. We can add these together. Oh, harmonic. Then you get your harmonics. This is going to be too complicated. But see, what we did is we're computing the beat frequency. So, you know, there's 200 hertz, and then there's like 400 hertz, and then sometimes they add, and sometimes they subtract, and then. So that was decomposing this waveform into, so we're getting a square, we're getting more square, right? Square waves, so the secret is, right, square wave is the hardest one to make, because in nature, actually everything can be decomposed into sine waves. You need a lot of frequencies to do that. Okay, so you guys have some, we're done with this module. Next time we start on a nice break on memory so you guys can start your extra credit if it's open. Is it working?